Okay, welcome students to this session number 24 in the subject of industrial metallurgy. These are what we are going to cover in this session. So in the last two sessions, we have been discussing about this defect or phenomenon which occurs in type 1 systems because of rapid cooling rates followed to bring down the castings to room temperature. So if you have done non-equilibrium cooling for a type 1 system, and because of that rapid cooling that you have followed, this defect called interdendritic segregation or coring has appeared in your alloy, then following are the ill effects, following are the consequences which would be seen in your alloy under room temperature conditions. You see, if the system is suffering from this defect called coring, uh, the system, the alloy system that has been obtained at room temperature is not having uniform chemical composition throughout the microstructure, throughout the material. As we have repeatedly said in the earlier two sessions, the core of the grains would be rich in one type of an element, and the regions close to the grain boundaries would be rich in the other constituents. So they'll not be homogeneously distributed, rather they'll have their own centers of concentration. So because your alloy is not having uniform chemical composition throughout, it's very obvious that its physical and mechanical properties will not be uniform or homogeneous everywhere. And this type of an alloy which has got non-uniform physical mechanical properties throughout its cross section, it's not a true alloy and cannot be put to industrial use. Not only this, because a true alloy has not been obtained, this alloy, this casting that has been obtained by you at the room temperature would be very poor in strength. It would be very poor in ductility. So the core structure is always weak and brittle. Also, it has been found that because a true alloy didn't get formed at the grain boundaries, it's not that you have a proper homogeneous solution of the two constituent elements. Rather, at the grain boundaries areas near the outer fringes of the grains, you have more of the lower melting point constituent element. And if that lower melting point constituent element was attacked even when that element existed independently, and so if that element was attacked by some particular corrosive agent, that corrosive agent will still continue to attack that constituent because it's lying independently or in excess at the grain boundary, so it's not behaving like an alloy. So these type of systems which have coring defect in them are more susceptible to corrosion, and corrosion which starts typically at the grain boundaries, because at the grain boundaries the element which the lower melting point element is lying, and if that lower melting point element, when it was existing as a pure element, was attacked by some special corrosive agents, it would still be attacked by them. So the alloy is not a commercially useful alloy if it is suffering from coring, and you must get rid of this problem. So why did coring occur? Now the question is, how do we eliminate or at least reduce coring? The question is that why did coring occur in the first place? The answer is, sir, coring occurred because we resorted to rapid cooling. We resorted to non-equilibrium cooling. So what seems to be the obvious answer? The obvious answer which seems to be to this problem is that, sir, don't do rapid cooling. Do equilibrium cooling and you will not find coring. But then, my dear students, that is not the solution to the problem. The problem number one this with this slow cooling option is that with slow cooling, see, right from say 1000 degrees centigrade, you have to come to 25 degrees centigrade, and if you start following cooling rates of the order of 25 degrees centigrade per hour or 10 degrees centigrade per hour, which are deemed as fit as equilibrium cooling, please see how when one lot of casting would come from that 1000 degrees centigrade to room temperature. So because this option is very, very unproductive, non-productive industry is never going to follow this option. So this is not a viable option because it's not economical. Slow cooling is not an appropriate route because it would hit the productivity of the firm like anything. But then if you say that, sir, no options, we have very limited orders with us, time is not an issue with us, still you cannot use slow cooling as a method to eliminate coring or to save yourself or to save your material from getting cored. Why? Because if you do slow cooling, please imagine that your casting would remain exposed at high temperatures for a very, very long period of time. And during those long periods of exposures at high temperatures, the, the grain size would grow considerably. And finally, at the room temperature, the casting that you will get, the type 1 alloy that you will get would be very coarse grained. And mind you, students, we'll do it in the lectures to come, that mechanical properties are, most of the mechanical properties are good when the grain size is fine. And as the grain size grows, properties deteriorate. So even if you can, if you have ample of time at your disposal and you say, sir, we can do slow cooling, still slow cooling should not be done, because with slow cooling rates, coarse grained structure would be formed in the steel, which would lead to inferior mechanical properties. And students, point number 3, in some cases, it's actually not possible to do slow cooling. If you are a factory and if you have a setup which does your casting through chill casting, how would you do slow cooling? So in some cases, it would not be possible for you to do slow cooling, right? So because of these reasons, slow cooling is never a method to get rid of coring. So you always do rapid cooling, you always do non-equilibrium cooling, you always allow coring to happen in your system, and then you do a subsequent treatment through which coring can be eliminated. And that subsequent treatment is called, the practical method of eliminating coring or reducing the effects of coring is called homogenizing or homogenization annealing. This is also referred to as equalization. What do we do in this process? We take the cored casting at the room temperature, we heat it to a specific temperature which is called the heat treatment temperature or the annealing temperature, and we'll discuss as to what should be this temperature. After having reached this temperature, we soak the casting at this temperature for some period of time. How long this time period has to be will depend upon the extent of coring and also on the type of material system that you have taken. Finally, after this soaking or holding at this heat treatment temperature is over, we cool down the casting or the coring at a very slow rate down till the room temperature. And by following these 3 simple steps, ample of diffusion takes place in your cored system. Diffusion actively takes place and it removes all segregated zones. So time temperature combination is selected, which ensures that enough diffusion occurs to eliminate all segregated zones. So I'll show you the time temperature diagram for this homogenization annealing treatment. So we have heated the steel till the heat treatment temperature. We have soaked the cold casting, not steel whatsoever. We have heated the cold casting of type 1 system to the heat treatment temperature. We soak it at this temperature for some period of time, and after that soaking period, time period is over, we slowly cool the steel down till the room temperature. Now mind it, this heat treatment temperature has to be a temperature which is high enough where diffusion in this material system can occur, but this has to be sufficiently below this effective solidus temperature. Students, mind it, sufficiently below the effective solidus temperature, not the solidus temperature. We are not talking about the equilibrium solidus temperature that would come from the equilibrium diagram. Rather, we should know what is the non-equilibrium solidus temperature of that alloy. So when we had cooled that alloy, we must note down this temperature. At this temperature, the casting would have actually solidified completely. And when we reheat the casting, we should remain sufficiently below it, and we should remain sufficiently at a high temperature where diffusion can take place. So this heat treatment temperature has to be very judiciously selected, high enough to cause diffusion, low enough to be away from this TES, right? And why? See, if by mistake you reheat your casting and come to a temperature close to the effective solidus temperature, it has been observed that the mechanical properties, particularly toughness and ductility of the type 1 alloy, gets severely impaired, and the problem is called overheating. So students, I repeat, if you are still below TES, but you during homogenization annealing you remain below TES but have gone pretty close to it, a problem, a defect called overheating occurs. After you have completed your homogenization annealing treatment, but this in this wrong way where you reheated pretty close to the TES temperature, cored casting, the coring problem would go, but a newer problem would come into picture, that ductility and toughness of your casting would get impaired. Another blunder that you can make is that you did not know that I have to be below TES. Rather, you thought that I have to be below the equilibrium solidus temperature, and with that confusion or that mistake, during reheating you choose your heat treatment temperature to be somewhere above TES, below TS but above, then liquid phase would appear, because typically the effective solidus temperature is this. So if you go beyond this temperature, liquid phase will appear at the grain boundaries of the type 1 system. A defect called burning would take place, and if this burning takes place, it completely ruins all the mechanical properties of your steel, which cannot be salvaged, which cannot be restored by any subsequent treatment, and you'll have to scrap your material. On the contrary, if overheating would have occurred, whatsoever mechanical properties of ductility and toughness have been lost because of overheating, they can be restored through a subsequent heat treatment or by cold working, etc., etc. But if you by mistake do burning, you go beyond TES, then the material has to be scrapped. It will have to be remelted, casted, and then only the remedy would be there. So that was all about overheating versus burning. I hope you have understood the things that I have tried to explain to you in this session. Thank you so much for being there.